Hi everyone, let's do section 6.2 on the law of cosines. And again, I'll be nice. I'll tell you when you can use the law of cosines, although later instructors may expect you to know when you can use it. Same setup as before. You have the letters facing each other. Little a faces or opposes big A, B faces B, C faces C, and so forth. Well, here's the bottom line. You have to remember this formula. It should look very familiar. C squared equals a squared plus b squared. That smells like whom? That smells like Mr. Pythagoras, and there's a reason for that. And then this fudge term, minus 2ab cosine of cap C. Right. Now, what happens if capital C is a right angle? Okay, so what if we do have a right triangle where we make capital C the right angle? Well, then what's the cosine of 90 degrees? Remember, COS, or the x-coordinate up here. What's the cosine of 90 degrees? It is 0. So this term completely dies, and we get, lo and behold, the Pythagorean theorem, right? Here's little c, here's little a, here's little b. C squared equals a squared plus b squared. So in the case where capital C is a right angle, and this is really a hypotenuse, then we have our classic Pythagorean theorem. In fact, you can think of the law of cosines as a generalization of the Pythagorean theorem. This generalizes the Pythagorean theorem to all triangles. The Pythagorean theorem only applies to right triangles, where you have a right angle and a hypotenuse. But the law of cosines generalizes the Pythagorean theorem to all triangles, like this guy. Or you could think of the Pythagorean theorem as a special case. The Pythagorean theorem is a special case of the law of cosines over here. But the law of cosines is like the Pythagorean theorem for all triangles, not just right triangles. So for memorization purposes, sure, the Pythagorean theorem helps. This looks like the Pythagorean theorem, except there's a third term, this fudge term here, which accounts for the fact that capital C may not be a right angle. The further away this is away from a right angle, then the more of an impact this fudge term is going to have. So we get that the square of one side equals the sum of the squares of the other two sides minus twice the product of these sides, okay, times the cosine of the angle between them. This letter is the capital version of this letter. A and B are symmetric here in the sense that I don't care which leg is A and which leg is B. By the way, these are not legs if it's not a right triangle. But basically, the idea is that C is one side, and you know, if it's not a right triangle, then C is not even the hypotenuse. There's nothing special necessarily about little c. But C squared will equal A squared plus B squared minus twice the product times the cosine of the angle facing the side of interest. Again, A and B are symmetric in the sense that you can switch these and it won't matter. So basically, if C goes from a right angle and shrinks down to an acute angle, little c will be smaller. And you can see that in the formula. If the angle is acute, then you're subtracting a positive value, and then C squared, and therefore C will shrink as we go from here to here. But if the right angle expands to an obtuse angle, then the hypotenuse gets longer. The hypotenuse becomes a longer side. If C is obtuse, then the cosine is negative, which means that the fudge term is positive because you have the minus sign there. C squared grows, therefore C grows. So you can do a thought experiment, and you can see why this minus sign makes sense. Of course, in the case of a right angle for capital C, this is 0. We get the Pythagorean theorem. But this all makes sense. Now, by using a similar proof, you basically have a similar pattern here. There's a certain symmetry among these formulas. So again, A squared, the square of one side, equals the sum of the squares of the other two sides minus twice the product of these side lengths times the cosine of the angle between them. This letter is the capital version of this letter on the left. Again, over here, b squared equals a squared plus c squared, the sum of the squares of the other two side lengths, minus twice the product of the side lengths, times the cosine of the angle between them. This is the included side for a and c, but it opposes this side. Looking at our setup, okay, looking like over here. In fact, I'll go way back here. I'll go way back to the original one that we focused on, all right? Going back to this guy over here, remember that capital C faces little c. And it's the included angle between these other two side lengths. All right. So again, over here, b squared equals the sum of the squares of the other two side lengths minus twice those lengths times the cosine of the angle included between them, which faces the side or the side squared of interest on the left. Now, you could solve for, up here, you could solve for cosine of cap C. Down here, you could solve for cosine of cap A and cosine of cap B, and you can get these variations. So you could say there are 6 or 9 laws of cosines, but they all ultimately come from memorizing this. If you can memorize this, then you basically know the law of cosines. Again, you follow similar patterns to get the other two versions for a squared and b squared. And let's say that you're curious to find c. Well, you can find c very quickly if you have SAS information, meaning that you know two side lengths and the angle included between them. So for this formula, if you know two side lengths and the included angle, you can plug this information into the right-hand side. You can quickly get c squared and then c. Now, when you solve for cosine of the angle, and you get these 3 variations, then these are ideal for SSS setups, where you're given 3 side lengths for a triangle. Then you plug in those side lengths. This side faces this angle of interest here. You can find these cosine values. By the way, I'm assuming that the 3 side lengths you're given will work. They will form the side lengths of a triangle. They will satisfy, for example, the triangle inequality. If I give you 3 pickup sticks, one is 3 meters long, one is 4 meters long, and one is 10 meters long. Can you form a triangle where you put these pickup sticks corner to corner? Nope, you cannot get a triangle because you're going to fail the triangle inequality. The detour would have to be longer than the straight line distance. Basically, these two sides won't be able to meet. Okay, a detour is never longer. Sorry, a detour is never shorter. A detour is never shorter than the third side. A detour has to be longer. 7 meters won't cut it. 7 meters, that's too short of a detour. That's shorter than the straight line length. Anyway, if you have appropriate SSS information, you can find the cosine of the angle. And in fact, if you're willing to use the inverse cosine notation, you can even come up with 3 more variations. Capitals from here, okay, cosine of cap C is all this. You could say that cap C is the inverse cosine of this, or arc cosine of this. Although books tend not to write this out. And you might ask, why not? I mean, you actually have this formula solved for an angle, like the angle for C, the measure of angle C. But here's the thing. Technically, books say that when you have an inverse sine, an inverse cosine, or an inverse tangent, the output should technically be measured in radians. And I think one reason why some textbooks don't write these variations is because we deal so often with degrees. Textbooks don't like to put this notation if we're going to write our answer in degree form. Personally, I don't have a problem with that. So even though we're going to give the angle measures in degree measures, typically in this chapter, I'm okay with using this inverse cosine notation, even though books normally expect a radian measure for output. I say degrees are okay. It's okay to work out an inverse cosine expression and you give the answer to me in degree form, provided you indicate the degree symbol. So there are 9 variations. But again, you really just have to memorize the very first one. So again, the logic, memorize the very first one. It looks a lot like the Pythagorean theorem, but there's a fudge term over here. And then from symbolic symmetry, you can get the other 2 versions for a squared and b squared. Don't forget to take the square root if you want c, a, or b. And then you solve for these cosine expressions. You can do it algebraically. You don't have to memorize to get these versions. And you can use the inverse cosine versions to get the last 3. So there are 9 versions of the law of cosines, but it all comes down to memorizing one and maybe doing some algebra. And again, the same checks work. Well, we can use the fact that angles have to add up to 180 degrees, and all the angles have to be strictly between 0 degrees and 180 degrees. Again, they add up to 180 degrees. The triangle inequality has to apply. Detours are never shorter. They have to be longer. And the eating rule has to apply. And again, the law of cosines, okay, they apply very well in the SSS case and the SAS case. So if you know 3 side lengths, then these versions are good. Then you can find the cosines of angles or the angles pretty quickly. And if you have SAS information, you can use formulas like these, including the Big Daddy, the C-square version. If you're given 2 side lengths and the included angle between them, which has the same letter as this guy. Now, once you know the games involved here, right, all these games here, then the examples are very straightforward. So in the SAS case, I give you 2 side lengths and the included angle between them. So all 3 letters are represented. We can solve the triangle. So I'm giving you the pieces in black, 2 side lengths and the included angle. So SAS, I'm giving you SAS information. Find the other parts. I just have one angle. I can't use the 180 degree rule yet for the sum, but we can find the 3rd side length, for example, by using the law of cosines. B squared, here's the unknown, B squared equals the sum of the squares of the other 2 sides, so A squared plus B squared minus twice AC times the cosine of big B. Plug in, make sure you're in degree mode, and do not combine these right off the bat. A lot of students love to do that because they love to combine integers. Do not combine those. Remember, the cosine of 70 degrees attaches to these, and we have a single term inside the radicand here. Do not bring these in. Do not combine these in with this. These coefficients apply to the cosine value. So these should not be touching these over here. You get about 7.08 centimeters. You might want to keep the whole version in your calculator in memory. But to 2 decimal places, to the nearest hundredth of a centimeter, B is about 7.08 centimeters. Maybe I should type it. B is about 7.08 centimeters. Again, you may want the more full version on your calculator in memory. It's not exact, but you'll get a better approximation on your calculator. Again, do not combine these. Do not blend these together. These guys go with him. All right. And then you can use the SSS versions. Since we have the 3 side lengths, you might want the better approximation for B. So use for what's in your calculator. Some books might suggest blending in the law of sines, but I think that's confusing. I think it's more straightforward to just go straight with the law of cosines, even though it might be a bit more work. All right, work this out. Make sure to process the numerator before dividing, and it's a triple division. You're dividing by all three of these. So either take the product first, or remember, it's a triple division. It's the numerator divided by this and this and this. It's a triple division. You might not want to round off. You might want to keep the full entry in your calculator display, all the digits. Okay, cosine of A is all that. So the inverse cosine, A is the inverse cosine of all this, right? A is the inverse cosine of all that. A is about 41.6 degrees. So this here is about 41.6 degrees, about. All right, and then now, how do we find angle C? We're given this. We now have this over here. We can use the 180 rule. 180 degrees minus that, about 68.4 degrees. It's easy to find that third angle once you find the other two. We're given one, and we found a second one. All right, so some quick checks here. Well, we made it so these added up to 180 degrees. You could double check that these add up to basically 180 degrees, up to rounding error. How about the triangle inequality? Well, this plus this is greater than 5 centimeters. This plus this is greater than that thing. This plus this is greater than that. So all the detours are longer. And also the eating rule. The smallest angle, capital A, faces the shortest side, 5 centimeters. The medium angle, capital C, okay, faces this medium side length, 7 centimeters. The largest angle faces the longest side, about 7.08 centimeters. But notice that we almost have an isosceles triangle. These degree measures are very close, so it makes sense that these side lengths are very close because it's almost an isosceles triangle. Some good checks there to make sure our answer makes common sense. For the SSS case, well, for two of the angles, you can use formulas for cosine of C and cosine of A, and you want the inverse cosine function to be able to figure out C and A. Plug in, you get these angles. How do we get the third angle? The 180 degree rule. Because remember, I'm giving you 3 side lengths. I'm not giving you any angles, but you can find 2 of the angles using variations on the law of cosines, and then you can find the third easily. Next up, a few comments about area formulas, optional.